Yes, and the very first feature that I'm going to present to you is the so-called AQ Workspaces. We have introduced with the release 16.10 a new concept which we call Workspaces, and a AQ Workspace will allow to save a complete analysis state of your AQ analysis, including all the results like this graph visualizations, the statistics, and the pure results, of course, but also the intermediate results, so that you are able later on to just resume to that analysis start and investigate your results or potential problems during the analysis. And I'd like to show you how this is actually working in the AQ. So let me open some prepared example. I have here a standard example, EDN. So this is how it looks like in the tool, as you know. And my first step is now I have here 3 analyses defined, 1 stack analysis, 1 timing profiler analysis, and 1 value analysis. And I'd like to do a start all analysis. So all of these items will be analyzed now. Next thing is that I could, for instance, jump to the result of the stack analysis and open the analysis graph. So let's see how it looks like. So this is the result of the stack usage analysis, so 1,400 bytes, and this is the call graph. I could also open the graph or the statistics of that analysis, for instance. So we see here an overview about the contributions of each routine to the overall stack usage and the global stack usages. So this is also an interesting result. I could, for instance, also do a disassembly of my timing profiler analysis here, so that I see the machine instructions of that entry point. Let's also open the local ICE file where I specify the clock rate and the context specification here. And last but not least, a report file. The report files are now always generated, so you do not have to specify a report file name in advance before doing the analysis. The report files will always be generated, and you can just, by clicking on that button here, open them. So you see all these results, including the reports and the disassembly here, are already opened. Finally, I'd like to also open the dwarf view here. Let me extract the dwarf debug information of the binary. And now I'm ready to store or to save my workspace. So let me just say here, via project, save as workspace. I'm allowed now to store that workspace file. It shares the same extension like the standard AQ project file, but the graphical user interface is perfectly able to distinguish between a standard project and a workspace file. So let us export or save that workspace file by clicking on that. And now I'm closing that project, and you see we have here generated that workspace file, which is much bigger than the standard project file, which just have the references. This workspace file contains all the results and the intermediate files. So by double-clicking on that workspace file later on, again, I will reopen the same state that I had before, you see. So all my results here of the analysis, here in the overview, you see the results, but also the output, the visualization, the statistics, even the disassembly and the opened ICE file and report files, as well as the dwarf debug information. All of them are directly opened, and you can continue with the analysis state where you left it before. So that is the first thing, but we also allow now to export the workspace when using the analysis in batch mode. So let me show you to you that as well. Let me discard that, and let's go back to the directory here. I remove that file again, and I'd like to just simply open that file and perform the analysis in batch mode. We are now using always the A launcher for the batch mode, and we specify the original project, and if we say export workspace, now providing a file name again, ednws apx. You see, all the analysis that we have done before will be done in the batch mode, also producing an workspace that we can resume afterwards. So that means if you want to do your analysis overnight, for instance, in batch mode, and you come back on the next day, you just have to do a double click on the exported workspace, and you can see what are the results. Without doing the analysis again, you can just double clicking on it and see what is the result and where are potential problems. All right, so this was the first feature. Let me now continue with the next one. This is also a feature that has been very often, many times wished by the customers. That is the generation of aiT annotations from various places in the graphic user interface, so from inside the graph or the message view, but also from the aiT editor. And I've prepared here a demo for it as well. Let me show you that. So I've here opened the famous scenarios example, and it comes with lots of analysis, prepared analysis, WCT, aiT analysis, TimingProfiler, and StackAnalyzer. And I've here the 1 millisecond task, for instance, in aiT. Let us have a look to that analysis more closely. So I just open that, run that, and we will see some problems here. There are unresolved computed calls in the analysis, one in the 1 millisecond task directly, and in the error hook. Okay, I can now say, well, let me show that in the call graph. So that's the location in the graph. Let me just fold that down to see a bit more infos here. I can double click on the basic block, and I see, well, indeed, there is a function pointer call via some variable called registered message handlers. It takes the handler component and calls that function. And you see there's this unresolved computed call node here. And now with the new release, we also print here some exclamation mark for that gives you a hint that there is some message, there's some problem, and a bulb symbol here, which indicates that there is some hint, some annotation hint for the same problem. I could now say, well, let us have a look to the message, to the connected message, which is the unresolved computed call message, and the hint is, well, to automatically generate an aiT annotation template. Before we do that, we would have to understand what is actually going on here. Well, the register message handler is called, and by clicking on the show source, we see where this comes from. Well, the register message handlers is initialized here with a message handler table, and this message handler table, well, is defined. Let us have a look to that in the sources. Is defined in a separate module. We can follow that. Here's the definition. And we see, well, it contains these 4 message handlers. Okay, so we just have to search for handle message, and we would see, and this would be the target of the computed call. So let us go back to the graph. We are now ready to generate the annotation. You just click on that icon and click on this bulb line here, and the annotation will automatically be generated in the local aiT annotation file, together with some placeholder, which is named here as targets. This placeholder allows you to do a double click on it, and then the symbol table will be extracted from the binary so that you can select your target routines that might be called at this function pointer call. We know it's these handle message routines, so we can just search for them, select them, click on OK, and the annotation will be completed by inserting the function pointer call targets. All right, so it is easier than before generating or producing these annotations. So let's redo the analysis the first problem has gone. We just have one problem left. It's the OS error hook. And well, you do not need to go via the graph. You can also say, I'm staying here in my message view. And well, here's the function pointer call. And it is related in the source file here. So here's the actual call. And the registered error handler was originally here defined or initialized for the user error handler. That means we can directly provide an annotation by also clicking here to either on that bulb here and say add annotation, or via the context menu add annotation. And by clicking on the message, well, the annotation will be generated again. So we already know that here the user error handler is called, so same procedure again, and the annotation will be completed. Okay. So now all computed calls have been resolved. The remaining problems are unbounded loops or recursions. And well, this is very similar. You can also say, well, let me show that in the graph. Here's the recursion. My OS error hook calls the user error handler, which may also again call back the error hook. So we have a classical recursion ring here. And I know that this recursion is just a virtual recursion because this back edge should never happen. So that means that the recursion is bounded by 1. I can simply say, well, let me produce the annotation here again from the graph, click on this integer placeholder and say 1, and the recursion will be bounded. Let us do the same for the loop bound. It's very similar. Right mouse click on the message here. We could, for instance, check what is my upper bound. Well, this is the for loop here, which is unbounded in the analysis, and it is obviously limited by that message length variable, and this message length has been set to 32 initially. So that means we can go back to the message, say add annotation, and click on 32. And the loop will be bounded. Okay, let's redo the analysis one last time. And well, the remaining loop, let us ignore them for now. What you can also do is, instead of just reacting on problems during analysis, you can proactively perform some actions, like, for instance, excluding routines from the analysis. And this is also easier than before. You can just do a right mouse click on routine, like, for instance, this OS shutdown here, and say, well, add annotation. And there is a pre-selected list of annotations, which will be increased in the next release as well. Let us now choose that shutdown should be made infeasible, because we are not interested in the worst case timing, including the shutdown procedure. So we say infeasible, and this annotation will be generated automatically, so that we have finally our worst case result here without the contribution of the shutdown. So you don't have to remember the syntax of the individual annotations. You can just generate them from the graph or the message view. And that's what I've not shown you yet. You can also generate some convenient annotations directly from the aiT annotation or aiT editor by right mouse click, insert aiT annotations, and all these annotations which have no connection to some some program location, these can be generated here, like a compiler or clock rate or context specification. All right, so this was the second feature. Next one is, well, the new loop bound view in the statistics. Let me go back to the tool, and if I open the statistics here, I have now a new, for TimingProfiler and for aiT, I have a new view that is called loop bounds that shows you what are the minimum and maximum bounds for every loop in the analyzed application. And this is not just a global loop bound overview, but a context-sensitive view. That means if you have several contexts in which the loop is executed, you will get an overview about the loop bounds per context. This is quite helpful information. And of course, you also see the so far unbounded loops, like the open socket L1. This is what I've left here, unbounded. You can of course also do right mouse click here and say add annotation loop bounds. And in this case, the open socket L1 is a busy waiting loop. So let's take the second suggestion here. And the busy waiting loop is typically annotated by providing the worst case timing instead of a worst case iteration count. So you could say, well, it takes 5 microseconds, for instance, and then this loop will also be bounded. So we have solved every problem in the analysis now by just generating the annotations from the graphic user interface. All right, so next thing which we have built is the so-called project file generator. It was already available from the information views, and now it is also available from the built-in editors. So let me just give you a short reminder. This looks like this. You have here the symbols table, for instance. You can say, well, I'm interested in all tasks, and I'd like to generate entry points or analysis items for these selected items, for these selected tasks. You could say right mouse click, create analysis, and for instance, timing profiler analysis. What is new is that you have this new dialog box that is opened, allows you to specify a certain pattern here with these placeholders. You can say, well, my analysis ID shall be constructed by the analysis type, which is now timing profiler, underbar, and then the name of the selected symbol. You could extend that as you want, and what you also could say is, for instance, let me also always generate a report file name underbar report.txt, for instance, and the same for the XML. And if I now say click on OK, these new 3 analysis items will be generated in the project file with the corresponding report files that we have provided via this pattern. So this was, except for the new dialog box with these nice patterns, this was already available, but now you can also go to every arbitrary ICE file. So in some editor file, you could say, well, I have here a list of entry points. Let me just copy that here. And go back to the ICE file. So, well, then I just replace here my, say it's a regular expression here, and I replace the prefix here, which is that, I guess. I replace that by this empty file here, and I also replace here, let me just remove that, this WCET by nothing. This was a remaining artifact. So I have a clear list of entry points, and now I could also say create analysis from that list here. Could say StackAnalyzer, and the same dialog will appear. And well, you could have that here as well, for instance. Okay, so this is also a new feature in ACube. What is also new is the stack area specification, which makes the analysis in general more precise. So let us have a look to that here. Let me just remove that again. Going back to that. If you go to the setup hardware, there's now not only the initial stack pointer address field, but it allows you also to provide a stack area. That means the area in which the stack usually operates. If you provide that area here, for instance, this one is a wrong one. You will make the analysis, the value analysis in general more precise. You see, we now get a contradiction because my stack pointer originally lies in a different area. But this area will always be considered to be restricted with all memory accesses that are related to stack pointer accesses. So even if the stack pointer is lost somewhere, the stack pointer value, it will always be restricted with this stack area. That makes the analysis precision more precise. And instead of just providing addresses, you can also say, well, let me take some symbols. If you have some symbol in a symbol table that points to your stack pointer, this can also be used here. -4, for instance, then because usually the stack symbol points to the end of the stack area, -4, then you should be aligned. And this can also be used now in the project file, the hardware specification. All right, so the Jenkins plugin, Daniel mentioned it already. It's available for Astray and Cube, and I'd like to shortly demonstrate that to you too. So the Jenkins platform looks like this. So Jenkins is the world's leading continuous integration platform, where people have software build projects set up, and now the Astray analysis, but also the ACube analysis, can be seen as a separate build step. And as soon as you have some problems, in case of Astray, some alarms or some definite runtime errors, and in ACube, some analysis problems, warnings or errors, then you can let fail this build process in the Jenkins build step. And it's very easily configurable. So you just say manage Jenkins, and you download the plugin from the plugin site, the official Jenkins plugin site. So you just go to available and search for AbsInt, and you will find it, because I've installed it here already. The AbsInt Astray and the ACube Jenkins plugin is not shown in the available section. But you can simply, by just clicking on that install button under available, you install that Jenkins plugin. And then, if you have set up some build project here, like this here, you can just say, well, configure my build and add the analysis as a separate build step. I've added it here. You would say here Astray analysis run or ACube analysis run, and then you get a new build step. You provide here the APX, some further options, for instance, to export Workspace when you have done the analysis. You click on apply, then it will be saved, and just build now. We just build now. We see what happens. Well, the software build process is started, and the analysis will also be done at the very end. So we can go to the console, and you see that the AbsInt ACube Jenkins plugin has been started here with a certain project file, and when the analysis has finished, we will get some result overview here. Also visualized. So you see here, this was the project with several stack and timing profile analysis. All of them were okay, no warnings, no errors. So the analysis run succeeded, and so the whole build process succeeded. But if you have a software build here which has a fail, we will see how this looks like. This will be now built. We can go to the console again. This is running in the background. All right, and well, the very last analysis here, this timing profile analysis, failed because our expectation here was 95 microseconds, but the analysis result actually was 98.63. So this is obviously a problem, and this is here shown. Analysis run failed, and therefore the whole build step turned that result into failure. And the plugin also says, well, you might investigate that analysis, and you can simply do that because we have exported the workspace by just copy that, going to your command line, paste that, open it, and well, the workspace file will be resume the analysis state. You see directly, well, this was the analysis that failed. I can do a double click on it and I see the result. So this is really a convenient way to investigate your automatically done analysis steps. All right, so this is the Jenkins plugin. And now finally, let me come back to the last feature here, the new AI's annotation features. I'd like to show it to you. The first thing is collect initializations. You maybe remember that new feature from the last release, that we are now able to collect variable initializations or values of these initializations in separate analysis, value analysis steps, which requires the ValueAnalyzer add-on. You could, for instance, say, well, let me collect initializations of these variables here, and then in a separate stack or timing analysis, you could reuse that initializations to have a more precise value analysis. And now we have extended that by also supporting the following patterns. You can say collect initialization, and then you provide a structure variable, a global structured variable, and by just providing that dot here, that indicates to the analyzer to collect all the members or initializations for all these members, instead of just providing individual members here. That's, we think, a convenient way to collect this structure members initializations. Then the next thing is you could collect initializations for all variables of a certain type. You just provide a type pattern, and you put this type functor around it, and then the value analysis will collect initializations for all variables of that specified type. And as a shortcut, we have this special type, which you call function pointer type. If you say, well, let me collect initializations for all function pointer variables, you can simply do that by type function pointer, and then all your function pointer variables initializations will be collected automatically. That is new. The next new feature is the tail call annotation. So far, tail calls usually result in unresolved computed branch problems during the analysis, and then you have to identify them as tail calls. What you then have to annotate is typically to say type tail call, and then you provide a list of call targets. This is now we have provided a shortcut, which is the tail call annotation. You simply say instruction program point tail calls, and then you provide a target list. This is more convenient, we think. And last but not least, we introduced new functors like this end functor. Instead of saying address area plus width -1, which is the end endpoint of a memory area, you can just now use the end functor. And the offset is now also available, the offset functor. If you want to get the offset in bytes of a certain component in your structure variable, for instance, you can say offset ftable.data, and you will get the offset in bytes, which you can use in some further annotations. So that's it for the latest features in the 16.10 release for ASTRE and Acube, the binary-based analyzers. Of course, there are many more changes and many more new features which you can access by following our www.absint.com release notes sites, Acube and ASTRE 16.10. I hope it was interesting for you. Thank you very much for your time. If you have some more questions, please yeah, drop us an email or give us a call, and I think we will process that. Thank you very much.